Okay, let's talk about motion of a particle along a curve. Now in 3 space, remember we represented a space curve as r of t. And let's let the position of the particle at time t be represented as p f of t, g of t, h of t. So that'll give its position. The velocity vector will be given by v of t, and that's going to be the same as the first derivative of r. And the acceleration vector will represent it as a of t, and that's going to be r double prime of t, or v prime of t. And the speed will be the magnitude of v. So let's just draw a picture. Let's let this be the origin, and we have a curve here, and this is going to be our p position at time t. This is r of t, and our velocity is going to be in the same direction along the tangent line to the curve. So same direction as the tangent vector, and acceleration will be kind of pointing inwards, and we'll say that that's the acceleration vector. But you can draw that given a specific example. All right. So for an example, let's look at r of t equal to 4 cosine t over 2i plus 4 sine t over 2j. So v of t is going to be the first derivative of r, and that's going to be 4 times minus sine t over 2. I'm just taking the derivative of each of the components, and times a half I plus 4 cosine t over 2. Take the derivative of the inside as a half j. So that's going to be minus 2 sine t over 2i plus 2 cosine t over 2j. The magnitude of v is the speed, and that's going to be the square root of each one of those squared. But cosine squared plus sine squared, remember, is 1. So that's the square root of 4, which is 2. So this is telling us that the speed is constant for any time. The acceleration is the second derivative, and that's going to be times the half, so it's going to be minus cosine t over 2. I'm taking the derivative of r prime, or v, I, and then derivative of cosine is minus sine, then times a half, because you have to take the derivative of the inside, so minus sine t over 2j. The magnitude of a is going to be the square root of cosine squared t over 2 plus sine squared t over 2, which is 1. So the acceleration is constant, no matter what the time. If we look at the x and y components, x of t is 4 cosine t over 2, and y of t is 4 sine t over 2. We can square each one, add them together, and we're going to get 16 because cosine squared plus sine squared is 1. And that's a circle. So these are parametric equations for a circle. If we let t equal pi over 3, let's just take a specific example, then plugging in pi over 3 into the velocity gives us -1 square root of 3. And if you plug it into the acceleration, we get negative square root of 3 over 2, negative a half. So the direction angle of v at pi over 3 is tangent alpha. Let's say we'll use alpha, and that's negative square root of 3 over 2. That's y over x. So that tells us that alpha is 2 pi over 3, and the direction of acceleration at pi over 3 is tangent beta. Let's say that angle's beta, and that's y over x for the acceleration, and that tells us that beta is 7 pi over 6. Okay, and that has to be in quadrant 3 because x and y are both negative, so that's how I get it in quadrant 3. Right here, x, y, negative. So it's quadrant 3, and this one, x is negative, y is positive, that's quadrant 2. That's how I get 2 pi over 3. So if I draw a picture of this, I have a circle, radius is 4. Okay, the point, let's say the point is right here at pi over 3. The point's 2 square root of 3, 2. That's what x and y is when t is pi over 3. And so measured from this reference, we're going to do the reference angle. Here's v. This angle is going to be 2 pi over 3. And a is coming out like this. Let me do that in red. Is 7 pi over 6. So here's the a vector and the v vector, acceleration and the velocity vector. So, I mean, it's easy to draw pictures, and we know their length. V is 1, so I didn't quite draw that right, and acceleration is 1 and v is 2. So the velocity is twice as long as the acceleration vector. Let me fix that. Okay. Now also remember that t is the unit tangent vector. At P. S we'll say is the arc length. So we'll say S increases as T increases. Then we can say that R prime of T, the magnitude, is ds dt, and that's the same as the magnitude of V. And that's going to help us come up with an equation for acceleration. So ds dt is called the tangential component of the velocity vector. Actually, I don't need absolute value here because s, if it's increasing, it's positive. All right, well, let's, what we're going to do is come up with an equation. We know capital T is r prime of t over the magnitude r prime of t because it's the unit tangent vector, and we know the normal vector, unit normal vector is t prime over the magnitude of t prime. So from this first equation, we have r prime of t is the magnitude of r prime of t times t. And so when we take the second derivative, we use the chain rule. But t prime of t from here is t prime of t times n of t. And then we know, we're going to substitute this, we know the curvature is defined to be t prime of t, the magnitude of t divided by the magnitude of r prime. So we can replace t prime of t by, and we can replace this right here by the second derivative of s with respect to t. This tells us that t prime of t, the magnitude, is the magnitude of r prime times the curvature. So we're going to replace that here, and that's going to give us r prime squared times the curvature times the normal vector, the unit normal vector. So we have the acceleration is the second derivative of the arc length with respect to p times t plus this is ds dt squared times the curvature times the unit normal vector, and we can say that that is v prime times t plus, that's v squared k n. We're going to say that that's at, and this is an. This is the tangential component of A, and this is the normal component of A. Okay, and we know that the tangential component is related to the change in the speed, or the magnitude of v, and the normal component is related to the change in direction of v, because it has to do with the curvature. Let me check some. Okay. Okay, let's get some alternative formulas for these two things so we can find them in the future. We know t is v of t over the magnitude v of t. So we'll say that's v over script v, where script v is the magnitude of v, which is the speed. So we know that the velocity is the speed times the unit tangent vector. So when we cross v with a, we have v of t dotted with, not cross, dotted, sorry, v prime t plus curvature v squared n. That's what a is. and that's v prime t dotted with t, which is 1, because it's the unit tangent vector, and this is script v, and this is 0 because they're perpendicular. The tangent and normal vector are perpendicular. So this tells us that v dot a is the speed times the derivative of the speed. And we know at is v prime, so that's going to be v dot a over v, or r prime dotted with r double prime over the magnitude of r prime. Okay, so that's an important formula. And also that the normal component is going to be k b squared, which is the magnitude of r prime cross r double prime over r prime cubed times r prime squared, which is r prime cross r double prime over the magnitude of r prime, which is the velocity. So that's also important. So this gives us formulas for finding the tangential and the normal components of A. And you can look at the homework for some of the problems worked out.